Some comets tumble, others flare. But 3, I divided by Atlas did something no comet should ever do. It seemed to fight against gravity, hitting the brakes on its way to the sun. Then suddenly, it changed its mind and started accelerating. Before you click off and think this is rubbish, hear this. We have new images that confirm the phenomenon. Let me explain. First, it vented gas toward the sun, as if it was trying to slow itself down. Weeks later, it flipped 180 degrees, firing its jets the other way, exactly like a space engine activating from silence. Astronomers call it a jet inversion. Loeb calls it something worth losing sleep over. And tonight, so will we. Because if this was a controlled maneuver near perihelion, then someone or something just used our star as a slingshot. Stay until the end to understand what 3, I divided by Atlas, might be trying to tell us, about itself and about us. If these mysteries have you on edge, like they have me, don't just watch, join the hunt. Hit like and subscribe so you don't miss a single revelation as this story unfolds moment by moment in real time. Tell me in the comments where you're watching from, what time it is there, and whether you believe we're hearing the whole truth about what's unfolding above our heads. And if you want to keep this signal alive, share this video on X, Facebook, Reddit, or even just with the people who still look up at night. You are the reason we can keep following the impossible, and for that, thank you. What you're looking at is something no comet has done before. On your screen right now, 2 images sit side by side. The first, captured by the Hubble Space Telescope on July 21, 2025, shows a comet glowing with an unusual brightness, pointing directly toward the Sunday. The second image, taken weeks later by the Nordic Optical Telescope, NOT, shows the same object, but now its tail streams away from the sun, like every well-behaved comet should. Between these 2 moments, something changed. Something that shouldn't be possible happened to interstellar object 3, I divided by Atlas. The claim sounds simple enough to dismiss. Comets change all the time, right? They develop tails, they brighten, they fragment. We've watched their cosmic dance for centuries. But this is different. This object appears to have reversed its jet orientation entirely. In July, it was emitting material toward the sun, creating what astronomers call an anti-tail, a sun-facing glow that defied the usual physics of solar radiation pressure. Then, as summer turned to fall, observers watched that forward-facing emission fade while a new tail grew in the opposite direction, streaming away from our star, exactly as textbook physics predicts. You might be thinking this is just a viewing angle trick, some optical illusion created by Earth's changing position relative to the comet's trajectory. We see these perspective effects all the time in astronomy. But the scientists tracking 3I, divided by Atlas, have ruled out the simple explanations. The timing is wrong for a pure geometry effect. The composition of the material being shed changed between the 2 periods. The morphology, the technical term for the shape and structure of the tail, evolved in ways that suggest something intrinsic flipped inside this object. The Nordic Optical Telescope tracked this transformation through July, August, and September. Frame by frame, image by image, they documented the sun-facing jet growing fainter while the anti-solar tail strengthened and lengthened. This wasn't a sudden switch. It was a gradual transition, a slow reversal that played out over weeks. And that gradual nature is precisely what makes this so troubling for conventional explanations. Here's where we need to understand what we're actually seeing. When material jets off a comet, it carries momentum. It pushes. If you're shooting gas and dust toward the sun, you're creating thrust in that direction, which means you're slowing yourself down relative to your orbital motion. If you flip that jet to point away from the sun, you're now accelerating in the opposite direction. For an object on a precisely calculated trajectory, such a reversal should show up in its motion. The orbit should deviate from the purely gravitational path. But here's the puzzle. 3I divided by Atlas isn't showing significant non-gravitational acceleration. Its path matches what gravity alone predicts, within the margins of measurement error. That means either the jets are perfectly balanced, pushing equally in all directions so the forces cancel out, or the object is so massive that the recoil from its outgassing is negligible compared to its inertia, or something else entirely is going on. Astronomers have annotated these images with the geometry overlaid. Earth here, Sun there, comet following this trajectory. The viewing angle does change, yes. But when you correct for that perspective shift, when you account for how projection can fool the eye, the reversal remains. Something physical changed. The immediate question is whether we're witnessing normal comet behavior, just unusually dramatic, or whether 3I divided by Atlas is doing something that requires a different kind of explanation. The conservative interpretation suggests compositional changes as the comet heats up. Different ices sublimate at different temperatures. As the outer layers heat and vaporize, deeper layers with different chemical makeup get exposed. But there's another interpretation, one that sounds like science fiction, but comes from serious scientists publishing in peer-reviewed literature. What if this isn't random outgassing at all? What if the reversal is controlled, deliberate, a maneuver executed by an object that isn't entirely natural? If the sun-facing emission was braking thrust, and the subsequent away-facing tail is forward acceleration, timed around the comet's closest approach to the sun, then we're looking at behavior that resembles trajectory adjustment more than passive ice sublimation. The stakes here are larger than one unusual comet. If 3I divided by Atlas is natural but exhibiting behavior we've never documented, it expands our understanding. If it's something else, we're facing a discovery that would rank among the most consequential in human history. We have weeks, not years, to find out. The object reaches perihelion, its closest approach to the Sun, on October 29th, 2025. That's the moment of maximum heating, maximum stress, maximum activity. What happens to 3I divided by Atlas during that passage will either confirm it's an exotic but natural comet, or deepen the mystery into something that demands answers we're not ready to give. The numbers tell their own story, and that story starts with mass. Between July and October 2025, 3I divided by Atlas shed approximately 2 million metric tons of material into space. Think about that figure, the mass of roughly 3 Empire State Buildings evaporating into the void, carried away by solar heating in just a few months. Astronomers derive this number through careful measurement of brightness and composition. That mass loss creates thrust. It has to. Newton's third law. When a comet vents gas and dust, the nucleus recoils, like a rocket engine firing. For typical comets, this rocket effect is measurable. It shows up as deviations from the purely gravitational orbit. But 3I divided by Atlas shows minimal non-gravitational acceleration. Its trajectory matches what gravity alone predicts. This absence of detectable recoil places powerful constraints. Let me walk you through the calculation that reveals why this matters. If you know the rate at which mass is being ejected and you know the velocity of that material, you can calculate the thrust force. Thrust equals mass flow rate times exhaust velocity, the fundamental rocket equation for a comet. Take reasonable estimates for these velocities, multiply by the mass loss rate. You get a thrust force. Now calculate the acceleration that force would produce. Force divided by mass equals acceleration. And here's where the constraint bites. For the observed lack of orbital perturbation to make sense, the nucleus must be massive enough that this thrust barely budges it. The minimum mass estimate comes out to approximately 33 billion metric tons. 33 billion. The uncertainty range is large. But even accounting for those unknowns, the lower limit sits comfortably in the tens of billions of tons. What does an object with that mass look like? If you assume a density similar to typical comet nuclei, that porous mixture of ice, dust, and rock, the calculation suggests a body several kilometers across. Comet Hale-Bopp, that spectacular visitor from the mid-90 had a nucleus estimated at roughly 60 billion tons. Comet Halley, about 220 billion tons. 3I divided by Atlas sits on the lower end of that range, but still qualifies as a substantial body. Three scenarios could explain the minimal, non-gravitational acceleration. 1. The object is genuinely massive enough that its outgassing thrust is negligible. This is the straightforward interpretation, requiring nothing exotic, just a big comet. 2. The outgassing might be unusually symmetric, jets firing in multiple directions such that the net force averages close to zero. 3. Something non-cometary might be happening. That third option is where things get speculative. If 3I divided by Atlas were maneuvering using some controlled propulsion system, you'd want the thrust to be balanced or variable in ways that don't produce random orbital changes. The math doesn't prove this interpretation, but it doesn't rule it out either. And that's enough to keep the question alive. Compare this to Oumuamua, the first interstellar visitor. Oumuamua showed significant non-gravitational acceleration despite no detected outgassing, a puzzle that generated years of debate. 3. I divided by Atlas is much larger. It does show clear outgassing, but the absence of corresponding orbital changes, given that large mass loss, creates its own puzzle. What happens next depends on perihelion. The close solar passage will heat the nucleus to maximum temperature. If the mass loss rate increases dramatically, we'll get better constraints. The data collected in the next few weeks will either tighten these mass constraints or reveal new anomalies that demand explanation. The physics of ice, in its complexity and diversity, always holds the potential key to decoding the strangest behaviors of cold celestial bodies. And in the case of 3I divided by Atlas, the most natural conservative explanation, the one the scientific community considers first and most thoroughly, revolves around these familiar physical laws applied to a unique compositional scenario. Abraham Loeb and Andrew Quieto, two astronomers who have delved deeply into the data and theoretical models for 3I divided by Atlas, have proposed a detailed mechanism. Their model doesn't invoke mysterious forces or alien technology, but focuses on the change in chemical composition of the material sublimating from the comet's surface as it gets closer to the Sunday. This argument rests on a solid foundation of astrophysics and astrochemistry, concerning how different types of ice react to temperature and radiation. Let's dissect this mechanism. Starting with carbon dioxide, CO2, ice, commonly known as dry ice. This is a common volatile in the cold regions of our solar system and likely other star systems too. The key property of CO2 is that it sublimates transitions directly from solid, ice, to gas, without melting into a liquid at extremely low temperatures, much lower than the freezing point of water. Even at the chilly distances beyond 3 or 4 astronomical units, AU, from the Sun, far beyond Mars's orbit, where sunlight is feeble, that meager heat is still enough for CO2 molecules on the comet's surface to break their crystalline bonds and escape into space as gas. This process isn't just slow evaporation. The CO2 gas, once liberated, expands rapidly and forcefully into the vacuum of space. This expansion generates significant thrust, much like gas escaping from a rocket nozzle. This thrust is powerful enough to drag along small dust particles trapped within the CO2 ice matrix. Imagine these dust particles like tiny debris caught in a gas explosion. Once freed from the nucleus surface, these dust grains begin their own journey, subject to two main forces: the sun's weak gravity pulling them in, and solar radiation pressure, the constant push from photons of sunlight pushing them away. For small dust particles, radiation pressure usually wins. Now, picture the scenario as Comet 3I divided by Atlas moves deeper into the solar system, getting closer to the warmth of our temporary host star. The surface temperature rises. The sublimation rate of CO2 skyrockets. But the CO2 ice layer on the surface, perhaps just a thin crust formed or accumulated during its long interstellar journey, is not infinite. Under the increasing heat, this CO2 layer will gradually deplete, like a thin layer of snow melting away under the sun, revealing the ground beneath. As the CO2 layer disappears, the material lying deeper within the comet's nucleus becomes directly exposed to solar radiation. And this deeper material, according to the model, has a significantly different chemical composition. It's predominantly water, H2O, ice, the most common ice in solar system comets, mixed with a large proportion of refractory dust. These are solid particles, silicates, carbon, complex organic compounds that do not sublimate at the temperatures the comet experiences. They are like pebbles and sand frozen within a giant block of water ice. Water ice, unlike CO2, requires significantly higher temperatures to sublimate effectively. It only truly activates strongly when the comet gets much closer to the Sun, typically inside Mars's orbit, around 1.5 AU, where the received heat is intense enough to break the strong hydrogen bonds holding water molecules together in the ice lattice. When water ice begins to sublimate violently, it also releases the refractory dust trapped within. But this process has crucial differences compared to the CO2 phase. Dust composition. Refractory dust might have a different grain size distribution than the dust carried by CO2. There might be more larger, heavier particles. Release velocity. Water vapor expanding into space might not be as energetic as CO2 gas due to molecular mass and temperature, potentially leading to lower escape velocities for the dust particles. Optical properties. Refractory dust is often darker and has different light scattering properties compared to small, bright, ice-coated dust grains. And here lies the crucial point, where Loeb and Kiato's model becomes particularly elegant in explaining the apparent reversal. They argue that this transition from a CO2-dominated outgassing phase to a water-dominated phase can flip the apparent direction of emission that we observe, not because the comet physically changes its thrust direction, but because the type of particle and how it interacts with sunlight changes from our perspective. CO2 phase. Distant July. When CO2 is the main driver, it releases a large number of small, possibly still ice-coated dust grains. These small, bright grains tend to scatter sunlight forward scattering, very effectively. This means that when we view the comet from a certain angle, like Earth's position in July, much of the light we receive from these particles is sunlight that has been scattered at a small angle relative to the original direction of sunlight. This effect, combined with the orbital geometry, can create a bright, concentrated halo that appears on the sunward side of the nucleus, forming the so-called anti-tail. It's not material flying towards the sun, but rather light scattered from outflowing material that is brightest when viewed from that specific angle. Water phase. Closer, September onward. As the comet gets closer, water ice sublimates strongly, releasing larger, darker, refractory dust particles. These larger particles are clearly pushed away by solar radiation pressure. They scatter light more effectively backward, backscattering, meaning they reflect sunlight back closer to the direction it came from. As a result, we see a more traditional, diffuse, longer tail pointing directly away from the sunday. Simultaneously, as the CO2 depletes and the small ice grains rapidly sublimate or are blown away, the bright anti-tail halo fades and disappears. The timing of this transition provides strong support for the model. 3I divided by Atlas was precisely in the distance range, 3 to 4 AU decreasing to below 3 AU, where the switch from CO2 to H2O dominance is expected to occur when the tail reversal observations were made. It didn't happen inexplicably early or late. This model isn't entirely novel. It builds upon solid precedent from observing hundreds of comets within our solar system. Astronomers are familiar with comets exhibiting complex activity variations. Some show seasonal outbursts as their poles tilt towards the Sun at different points in their orbit. The giant comet Hale-Bopp 1997 was a classic example, displaying multiple distinct jets erupting from different active regions on its non-uniform nucleus surface. Each jet could have slightly different chemical compositions and activity schedules. Comet 67P, divided by Churyumov-Gerasimenko, studied up close by the Rosetta spacecraft. also revealed an incredibly diverse surface with distinct regions varying significantly in activity and composition. The lesson learned is that comet nuclei are not uniform ice balls. They are complex, heterogeneous mini-worlds like cosmic onions with multiple layers or rubble piles stuck together containing different mixtures of ices and rock. As thermal waves from the sun penetrate inwards, different layers and regions can activate at different times, producing complex and sometimes surprising outgassing behaviors. Furthermore, this model isn't just a plausible story. It makes specific, testable predictions. Clear spectral change. This is the most critical prediction. If the mechanism is a CO2 to H2O transition, the comet's spectrum, light analyzed by wavelength, must reflect that. Specifically, early phase, July. Emission lines or absorption bands related to CO2 or its daughter products like CO should be relatively strong compared to lines from H2O or its daughter product OH. Later phase, September onward, this ratio should invert. Emission lines of OH, the signature of water, should become clearly dominant, while the CO2 signal might weaken or change character. Infrared observations, like from JWST, are particularly sensitive to these molecules and could quantify their ratios precisely. Change in dust to gas ratio. The water phase is expected to release more refractory dust compared to the CO2 phase, which might produce more small ice grains. Therefore, the ratio between the total amount of dust and the total amount of gas being emitted, dust-to-gas ratio, might change over time, which could be measured through multi-wavelength observations. Change in dust properties. Polarimetry measurements could potentially reveal changes in the average size, shape, or composition of the dust particles between the two phases, consistent with a shift from small ice grains to larger refractory particles. And indeed, some early observational evidence seems to support this picture. Preliminary reports from astronomers monitoring 3 I divided by Atlas have mentioned detecting spectroscopic compositional changes consistent with evolving volatile activity over time. The relative strengths of different emission lines, for example between CN, C2, and OH radicals, appear to have shifted in a manner consistent with different ice species activating sequentially as the comet warmed up. However, it is crucial to acknowledge the weaknesses and uncertainties inherent in this model, as with any scientific model under scrutiny. Inferred internal structure. The assumption of a distinct layered structure, CO2 outside, H2O inside, is a reasonable simplification but remains unproven. The actual structure could be much more complex, with pockets of CO2 ice interspersed or uneven active regions, which could complicate the transition process. We are inferring internal structure from external behavior, and there's always a risk that multiple different structures could produce the same observed behavior, the uniqueness problem. Influence of anisotropy and rotation. Simple models often assume outgassing is uniform, isotropic, or follows a simple pattern, but real comets often outgas from narrow, concentrated jets. The direction and intensity of these jets are influenced by the rotation of the nucleus and surface topography. The interplay between rotation and asymmetric jets can create complex variations in brightness and morphology that might mimic or obscure underlying compositional changes. Dust parameter. Uncertainties. The model relies significantly on assumptions about the dust grain size distribution and their scattering properties in both phases. While these assumptions are reasonable based on knowledge of other comets, we lack direct measurements for 3I divided by Atlas. Errors in these dust parameters could affect the modeled appearance of the tail and anti-tail. Therefore, the composition-based model represents the most conservative, plausible, and likely explanation based on current astrophysical understanding. It doesn't require invoking exotic or non-natural factors. It's the starting point most comet scientists would use to try and understand 3I divided by Atlas. It aligns with much of the observational evidence and has precedent within the solar system. But the critical question remains: can this model fully account for all aspects of this strange behavior, especially the striking lack of significant non-gravitational acceleration despite losing a vast amount of mass? Is the compositional transition alone sufficient to explain the intensity and speed of the tail reversal? These are open questions, areas where the model might need refinement or supplementation. And it's precisely these lingering questions that open the door, however slightly, to considering other possibilities, as we will discuss next, even if they seem far more speculative. Now, we boldly step into the territory of speculation, but it's crucial to emphasize that we do so with the rigor of the scientific method, not the unchecked excitement of sensationalist news. Abraham Loeb and Adam Hibbard, not just through public statements, but also through published technical analyses, have courageously posed the question that most of the astronomical community tends to carefully avoid or discuss only privately. What if the observed jet reversal in 3I divided by Atlas is not a natural process at all? What if this object is executing a controlled maneuver, adjusting its trajectory, using some form of propulsion that only coincidentally resembles superficially the chaotic outgassing of a typical comet? This audacious hypothesis isn't baseless. It stems from interpreting the observed timing and directionality of the ejected material plume. The core argument goes like this. If the bright anti-tail, pointing towards the sun, observed in July, was indeed functioning as braking thrust, that is, generating a gentle push against the direction of orbital motion, slightly slowing the object as it plunged into the solar system, then the subsequent tail pointing away from the sun could represent forward thrust. This thrust, if strategically activated as the object swung past perihelion, would effectively accelerate it as it departed the sun's vicinity. This entire sequence, decelerating on approach, accelerating on departure, timed around the closest encounter with a major gravitational body, the sun, bears an uncanny resemblance to a deliberate trajectory adjustment or a gravity assist maneuver. This is a technique our own spacecraft frequently employ to efficiently alter velocity and trajectory by borrowing energy from the gravitational fields of planets. Could 3I divided by Atlas be doing the same, but with the sun? Before you hastily dismiss this as wild fantasy, simply because it evokes science fiction tropes, let's objectively consider what specific observational signatures would need to exist to lend support to such a radical hypothesis. Anomalous and sustained non-gravitational acceleration. This is the most critical factor. We would need to detect an acceleration, or deceleration, that cannot be explained solely by the sun's and planet's gravity, and this acceleration must be significantly different from what natural ice sublimation models predict. The difference could be in magnitude, thrust much stronger than the mass loss could generate; in duration, thrust continuing long after the comet should have cooled and ices stopped sublimating; or, in direction, thrust changing direction abruptly or in a way unrelated to solar illumination. Repeatable and non-natural reorientation of the jet axis. Natural comets can have multiple jets, but their direction is generally tied to fixed active regions on the nucleus surface and modulated by rotation and solar illumination angle. If 3I divided by Atlas demonstrated an ability to actively and repeatedly change the direction of its main thrust plume, especially in ways that cannot be explained by simple rotation and illumination models, that would be extremely suspicious. It would suggest a mechanism for orienting the thrust. Spectral anomalies, suggesting manufactured materials. Spectra are chemical fingerprints. If analysis of the light from 3I divided by Atlas revealed the presence of pure metals or alloys not typically found in natural cometary environments, for example refined aluminum, titanium, or complex organic compounds with structures only likely formed through industrial processes, or isotopic ratios drastically different from those produced in natural supernovae, that would constitute extremely strong evidence for a non-natural origin. Comets are primitive material. They shouldn't contain technological artifacts. So far, it must be stressed, no definitive, irrefutable, smoking gun signature among these has been detected. However, it's equally important that the observations remain incomplete and contain gaps. 3. I divided by Atlas is a faint object, moving incredibly fast across the sky, making continuous monitoring and high-quality data acquisition exceptionally difficult. There's always a possibility that brief, anomalous bursts of acceleration, fleeting changes in jet direction, or transient spectral features occurred precisely when no sufficiently powerful telescope was observing it. The principle of absence of evidence is not evidence of absence is particularly pertinent here, given the transient and elusive nature of the phenomenon. So, how do we scientifically test the engineered object hypothesis? It requires a long-term, systematic observation and analysis strategy. Ultra, precise, and long-term astrometric monitoring. This is fundamental. Astronomers need to continue measuring the position of 3I divided by Atlas with the highest possible accuracy, repeatedly over months, even years as it recedes. This positional data is then fed into complex orbital models. Scientists will compare the observed trajectory against a purely gravitational prediction. Residuals, the tiny differences between the actual and theoretical positions, will be meticulously analyzed. Small random residuals are expected due to measurement errors and weak, undirected outgassing, but large, systematic residuals, indicating a sustained thrust in a specific direction unexplained by sublimation models, would be a monumental signal. Detailed polarimetry. Light scattered by cometary dust is polarized. The way it's polarized depends on the size, shape, and composition of the dust grains. Natural cometary dust has fairly characteristic polarization signatures. If polarimetric measurements of 3I divided by Atlas reveal drastically different signatures, perhaps suggesting the presence of smooth metallic particles or regularly shaped structures, that would be another anomaly. High-resolution, multi-wavelength spectroscopy. Continue acquiring spectra with the highest possible resolution, especially in infrared wavelengths where molecules have clear signatures, for example, using JWST if feasible. Search for rare emission or absorption lines, unusual isotopic ratios, or compositional changes over time inconsistent with natural sublimation models. Sophisticated trajectory analysis. Is there anything peculiar about the orbit itself? Did it enter the solar system at an opportune angle or velocity? Natural interstellar objects are expected to arrive from random directions. While proving an orbit is designed based on just a few examples is extremely difficult statistically, if 3I divided by Atlas's path showed significant fine-tuning that seemed optimized for a close solar or Earth encounter, it would add to the suspicion, especially if combined with other evidence. The reaction of the scientific community to this radical hypothesis, as mentioned, has been mixed, but predominantly skeptical. This is entirely understandable. Science operates on the principle of Occam's razor, favoring the simplest explanation that fits the evidence. The history of astronomy is littered with initially baffling anomalies that were ultimately explained by known or newly discovered natural processes. Thus, the null hypothesis that 3I divided by Atlas is merely a natural comet, albeit a very strange one in its composition or structure, still carries a very strong prior probability. The burden of proof lies heavily on those proposing the extraordinary explanation. However, the counter-argument put forth by Loeb and collaborators also holds significant scientific merit. Dismissing a possibility simply because it seems unlikely without conducting rigorous tests is unscientific. Science progresses precisely by seriously considering hypotheses, even those on the fringe, and designing experiments or observations to objectively accept or reject them based on evidence. The discovery of extraterrestrial technology would be a civilization-altering event, arguably the most important discovery ever made. Its potential significance is so immense that, according to this argument, it justifies a level of scrutiny and resource allocation far beyond what would be given to more mundane hypotheses. The risk divided by benefit calculation here is unique. Risk of false positive, type Y error. Wasting time and resources studying a natural object mistakenly thought to be artificial. The cost is resource expenditure and perhaps some scientific embarrassment. Risk of false negative, type 2 error. missing the detection of actual extraterrestrial technology because we were too conservative, didn't consider the possibility seriously, or didn't allocate sufficient resources to test it. The cost is potentially missing a civilization-changing discovery. Many argue that, in this specific context, the cost of a false negative far outweighs the cost of a false positive, thus justifying thorough investigation even if the probability of success is low. For a claim like 3I divided by Atlas is artificial to gain acceptance, the evidence would need to be overwhelmingly strong and irrefutable. It would require multiple independent lines of evidence from different sources, all converging on the same conclusion: acceleration unexplainable by natural models, spectra showing manufactured materials, perhaps structured radio emissions. The standard of proof would need to be far higher than for typical discoveries, likely requiring a 5 sigma confidence level or more as used in particle physics. While waiting for such, perhaps never forthcoming, evidence, proposals for interceptor missions have been floated, primarily by Loeb and his team, but as stated, this is a monumental technological challenge. 3I divided by Atlas is moving too fast. Launching a spacecraft quickly enough to catch it would require advanced propulsion technologies, possibly nuclear or light sails, and an incredibly rapid political, divided by financial decision-making process almost impossible under current procedure. Fast flyby missions might be more technically feasible, but would only provide a fleeting glimpse. Therefore, the most realistic approach likely involves long-term remote observation and the most careful data analysis possible. The engineered probe hypothesis certainly feels like reading a science fiction novel, and quite possibly, that's all it is. Quite possibly, we are merely projecting human patterns of thought onto complex natural phenomena we don't fully comprehend yet. But the only way to know for sure is not to dismiss the idea outright, but to objectively gather more data, test the predictions of both hypotheses, natural and artificial, and let the evidence speak for itself, regardless of how surprising or disappointing the final answer might be. That is the very essence of the scientific method when confronting the unknown. And it applies equally whether we are studying mundane rocks, distant stars, or mysterious visitors from interstellar space that might be neither. The cosmic clock is ticking louder now. Each passing day brings us closer to the moment that will either rationally explain 3I divided by Atlas or deepen its mystery into enduring legend. Perihelion, the moment of closest approach to the Sun, arrives on October 29th, 2025. At that point, the comet will race past at about 1.356 astronomical units, roughly 203 million kilometers, from the Sunday. This distance, while still safely beyond Earth's orbit, is close enough for the Sun to become an immense furnace. Let's call this 3I divided by Atlas's crucible. This isn't just a point in orbit. It's the ultimate stress test. The moment of truth. The Sun's intense radiation and charged particle wind will batter the comet's nucleus with the maximum intensity it will experience during its journey through our solar system. If this object harbors volatile ices hidden deep beneath its surface, this fierce heat could trigger them, causing violent and unpredictable outbursts. Scientists will be searching spectra for the appearance of new molecules, ice species that only sublimate at high temperatures, potentially revealing the composition of its deeper interior. They'll also closely monitor any changes in its rotation rate, as uneven outgassing can act like tiny rocket engines, altering the nucleus's spin. Furthermore, if any structural weaknesses exist within the nucleus fractures, poorly consolidated material, the tremendous thermal stress, and internal gas pressure might exceed the breaking point. The result? The comet could disintegrate into fragments. Astronomers have witnessed other comets meet this dramatic end near the Sunday. Such spectacular breakups, while terminal for the comet, are golden opportunities to study the internal structure and composition normally hidden from view. Will 3I divided by Atlas withstand the heat? However, observing this critical moment presents significant observational challenges. The perihelion passage places 3 I divided by Atlas, relatively close to the Sun in the sky, as seen from Earth. This means the Sun's blinding glare will cause severe interference. Ground-based telescopes will have only extremely narrow windows during twilight, just before sunrise or just after sunset, when the comet is high enough above the horizon, but the Sun is sufficiently below. Every minute of observation during these windows is precious. Even powerful space observatories like the Hubble Space Telescope are constrained by strict solar avoidance angles to protect their sensitive optics. Scheduling observations of 3I divided by Atlas requires incredibly careful planning to catch the object when it's far enough from the Sun in the sky, yet still near perihelion to record peak activity. Special techniques, like using coronagraphs if possible, might be employed to mitigate the glare. And we also cannot overlook the potential data from the Mars flyby on October 3rd. Did the orbiters currently circling the red planet, especially the high-resolution high-rise camera on the Mars Reconnaissance Orbiter, MRO, manage to be redirected in time to capture images of 3I divided by Atlas? Reprogramming an interplanetary spacecraft for an unexpected target is extremely complex technically and procedurally, but if successful, those images would provide a completely different stereoscopic view compared to Earth-based perspectives. This alternative viewpoint could be key to distinguishing between true 3D structures in the outflow and misleading 2D projection effects, offering invaluable data for testing models. However, the greatest scientific payoff, the real hunt for answers, will likely occur after perihelion, as 3I divided by Atlas begins its journey back out into the cold darkness. Its brightness will initially remain very high, perhaps even brighter than on its inbound leg at the same distance. This is because the heat absorbed deep within the nucleus takes time to dissipate, sustaining outgassing activity for some period, even as the distance from the Sun increases. It is during this post-perihelion phase that the precision of astrometric measurements becomes more critical than ever. The task now is to measure the object's position with extreme accuracy, perhaps every few days, and compare its actual trajectory against the theoretical path it should follow if only gravity were acting on it after perihelion, based on its earlier orbit. If non-gravitational acceleration suddenly appears, strengthens, or changes direction systematically after passing the Sun, that would be extremely strong evidence that something physically significant happened during or because of the passage through the perihelion crucible. Was it the activation of new ice pockets, a structural change due to heat, or something else? Accurately quantifying the magnitude, direction, and duration of any non-gravitational acceleration will be key to distinguishing between natural models and non-natural hypotheses. And then, December 19th, 2025, another date to circle on the astronomical calendar. That's the day 3I divided by Atlas makes its closest approach to Earth. Although close, here is still a safe and vast distance, about 270 million kilometers, nearly twice the Earth-Sun distance. It will be the nearest this object gets to us in its known trajectory. Why is this important? Because the intensity of the signal, light infrared radiation, received from an object decreases with the square of the distance. Closest distance means the strongest signal. This is arguably our golden opportunity for the most detailed observations possible. The world's largest ground-based telescopes, like Keck, VLT, Subaru, can focus their immense light-gathering power to capture images with the highest resolution achievable from the ground, attempting to resolve fine structures in the coma, or maybe even the shape of the nucleus itself. More importantly, they can collect high-quality spectra, dissecting the light into its constituent colors to more accurately identify the molecules present and their abundances. And, of course, there's the James Webb Space Telescope, JWST. If its incredibly busy schedule allows for a precious window of observation time, JWST could be a game changer. Its unparalleled infrared capabilities can peer through obscuring dust, directly detect the spectral signatures of key molecules like water, H2O, carbon dioxide, CO2, carbon monoxide, CO, methane, CH4, and even more complex organic molecules. JWST also has the potential to measure isotopic ratios, for example, the deuterium divided by hydrogen, D divided by H ratio in water, a highly sensitive chemical fingerprint that could reveal clues about the environment where the comet formed, whether it was similar to or different from our own solar system. Thermal measurements of the nucleus temperature from infrared radiation could also be made. However, the observational journey is not without its perils. There will be dangerous periods, blackout periods, particularly when the comet enters solar conjunction from Earth's perspective. During these phases, the object becomes too close to the sun in the sky, making optical observations impossible and dangerous for instruments. These gaps in observational coverage are worrying because we risk missing crucial, transient events, like a brief outburst, a sudden change in tail morphology, or even a strange radio signal, things that might appear and vanish precisely when we are unable to see. The post-perihelion brightness evolution is also a major uncertainty and a crucial diagnostic. As the comet moves away from the sun, it will undoubtedly fade. But the rate at which it fades will tell a story. If it dims rapidly, it might suggest activity was confined to a thin surface layer or a relatively small nucleus. Conversely, if activity persists strongly for months, it could indicate a large nucleus with significant thermal inertia, heat stored deep inside, or the slow release of volatiles from deeper layers. The history of comet observations shows enormous variation in post-perihelion behavior, making prediction difficult but highlighting the value of continuous monitoring. Therefore, close coordination and rapid data sharing among observatories worldwide will be absolutely essential. Early warning networks, coordinated observing protocols, the flexible use of directors' discretionary time on major telescopes will all need to be leveraged to their fullest extent. By late December 2025, after collecting and analyzing months of crucial post-perihelion data, the picture of 3, I divided by Atlas, should become significantly clearer. The orbit will be determined with unprecedented precision. Spectroscopic changes will have documented the chemical evolution. High-resolution imaging will have recorded the morphological evolution of the tail and coma. The synthesis of all these data streams from multiple telescopes using multiple techniques must lead to one of two scenarios. They will either convincingly converge on a coherent, natural explanation, perhaps the compositional change model discussed earlier, or a more refined version of it, or they will leave behind residual anomalies, inconsistencies, ill-fitting pieces that natural models cannot easily accommodate. That convergence, or lack thereof, will entirely dictate the next chapter of this story. 3, I, divided by Atlas, will either become just another interesting data point, an extreme example of cometary diversity in the galaxy, or it will be the first signal, the first piece of evidence for something that completely reshapes our understanding of the cosmos and our place within it. The next few months are not merely a countdown to key astronomical events. They are a countdown to a potential decision point, a possible fork in the road in how we understand interstellar space and the possibility of uninvited visitors from the infinite darkness. However, before we venture too far into exotic speculation, there's a fundamental question, a healthy skepticism that every good scientist must address. Could this entire tail reversal be just an optical illusion? Could we simply be fooled by the viewing angle? Because not every strange thing in the sky is actually strange when you look closer. Sometimes, what appears extraordinary is simply ordinary physics viewed from an unusual angle, a trick of projection geometry. This is the first, and perhaps most important, lesson of observational astronomy. A lesson learned and relearned, sometimes painfully, over centuries of discovery. The apparent retrograde motion of Mars baffled ancient astronomers for centuries, until Copernicus's heliocentric model explained it as a simple perspective effect when Earth overtakes Mars in our orbits. The famous canals on Mars, once thought evidence of civilization, turned out to be optical illusions created by the human eye connecting random dark spots into lines. And more importantly, in the history of comet observation, there have been numerous instances where comets appeared to flip their tails or sprout a tail pointing towards the sun, when in reality, only our viewing angle from Earth changed as we moved through the comet's orbital plane. The question for 3I divided by Atlas, therefore, is fundamental and critically important. Are we truly witnessing an intrinsic jet reversal within the comet, a physical change in how it ejects material? Or are we just being deceived by a sophisticated projection illusion? This distinction carries enormous weight. An intrinsic flip demands a deep physical explanation. Something fundamental changed inside or on the comet, possibly related to composition, structure, or even deliberate activity. Conversely, a projection effect is merely geometry. It arises from the continuous change in the relative positions of Earth, the comet, and the Sun, creating the illusion of reversal, while the comet's actual eruption pattern might remain constant. Let me explain more clearly how a projection illusion can occur. A comet ejects material into three-dimensional 3D space, but we, from Earth, only observe its image projected onto the two-dimensional 2D plane of the sky. Our line of sight collapses depth information, making it extremely difficult to distinguish between material flying towards us, away from us, or perpendicular to our line of sight. As Earth orbits the Sun and the comet follows its own trajectory, in this case, a hyperbola, the viewing geometry, our perspective, changes constantly, day by day. Consequently, a fixed 3D structure, like a curved dust tail, can appear to change shape or even reverse direction as our viewing angle shifts. The classic and most relevant case here is the anti-tail phenomenon, known for over a century. An anti-tail is not actual material flying towards the sunday. It is usually formed by large, heavy dust particles that are less affected by solar radiation pressure. These particles tend to lag behind the nucleus along the comet's curved orbit, forming a thin sheet of dust spread out in the orbital plane. When Earth happens to pass through that orbital plane, we view this dust sheet edge-on. Due to perspective effects, this trailing dust sheet appears to point directly towards the Sun, creating the illusion of a forward-pointing spike or tail. Then, as Earth continues its motion and moves out of the comet's orbital plane, the viewing angle changes, and this geometric anti-tail fades and disappears, while the normal gas and small dust tail pushed away from the Sun becomes prominent. Astronomers are well aware of this effect and have sophisticated methods to distinguish between geometric anti-tails and true sunward physical structures, which are extremely rare. They use techniques like vector tomography, combining observations from multiple dates and viewing angles to try and reconstruct the actual 3D structure of the material around the comet. They can also use polarimetry. Cometary dust scatters sunlight and polarizes it. The degree and direction of polarization depend on the scattering angle, the angle between the Sun, the dust particle, and the observer. By measuring polarization over time, scientists can test whether the observed morphological changes are consistent with a static dust cloud being illuminated from different angles, or if it requires an actual redistribution of material. Now, let's apply these cautionary lessons to 3I divided by Atlas. Between July, when Hubble imaged the anti-tail, and September, when Not recorded the tail pointing away, Earth's position relative to the comet changed significantly. Both objects were moving on different orbits. The viewing geometry undoubtedly shifted, altering phase angles, scattering angles, and how any 3D structures, if present, were projected onto our 2D sky. The team at the Nordic Optical Telescope, NOT, who performed the detailed sequence capturing the transition, would certainly have been deeply aware of projection pitfalls. Their analysis almost certainly included detailed geometric modeling, carefully testing whether the observed changes could be explained solely by Earth's changing position. The fact that they concluded and reported an intrinsic jet reversal strongly suggests that their models ruled out pure projection effects as the primary cause. Perhaps the change was too abrupt, or the morphology too different from what a typical geometric anti-tail could produce. However, completely ruling it out is always difficult and depends on assumptions. Geometric models must assume an initial 3D dust distribution, ejection velocities, particle sizes, etc. Uncertainty in these assumptions always leaves a small loophole for alternative geometric explanations, however less probable they might seem. Nevertheless, there is another extremely important factor weighing against the pure projection illusion hypothesis: the change in chemical composition. As mentioned earlier, preliminary reports from spectroscopic follow-up suggest the chemical makeup of the material being emitted by 3I divided by Atlas did change during the period from July to September. Projection effects cannot change the chemical composition of matter. They only change how we see the distribution of that matter. If the spectra truly show a transition from a CO2-rich phase to an H2O-rich phase, then that constitutes strong evidence for a physical, intrinsic change happening on or within the comet, independent of our viewing angle. The risk of confirmation bias, the tendency to interpret new evidence in a way that confirms pre-existing beliefs or hypotheses, is always a factor to be wary of in science, especially when dealing with unusual phenomena. Could researchers be too eager to find something extraordinary that they overlook more subtle geometric explanations? This is why independent analysis by different teams and critical scrutiny from skeptical scientists are crucial parts of the process. But, based on the currently available information, the most honest and balanced assessment seems to be projection effects might have contributed partly to what was observed, perhaps exaggerating or altering the apparent shape of the structures. However, they seem unlikely to explain the full extent, the speed, and especially the accompanying chemical composition change associated with the observed tail reversal. Therefore, the conclusion that an intrinsic jet reversal occurred is likely correct, although lingering uncertainties remain and need further clarification through future observations and modeling. And it is precisely those residual uncertainties, however small, that are important. They keep the door slightly ajar, compelling us to look even closer at the nature of this physical change and how truly strange it is before settling on final explanations, especially potentially revolutionary ones.